On the morning of December 8th, a new set of images forced the scientific community to stop. Not because of what was missing, but because of what was suddenly there. For weeks, telescopes had tracked 3I Atlas as it moved past Jupiter, shedding mass in irregular pulses. But now, as light returned from a series of observatories and private stations, the structure that emerged wasn't weaker. It was sharper, more defined, and more confusing. The surface didn't blur into dust like a typical comet. It showed lines, edges, symmetry. One amateur captured a glow that seemed to pulse, not flare, and another recorded a shape that didn't match any known Coma model. The professionals checked the metadata twice. The image contrast was real. Something about 3I Atlas has changed, and the implications reach far beyond comet physics. This wasn't just a better view. This was a different object. Now, let's walk through the evidence. It didn't come from NASA. It didn't come from the James Webb Telescope, or from some billion-dollar observatory stationed in Earth's orbit. It came from a backyard, from a quiet hillside in northern Spain, from a man named Matteo Llorente, an electrical engineer by day and a passionate amateur astronomer by night. His telescope wasn't anything exotic, just a well-maintained 14-inch Newtonian reflector with a narrowband CCD camera and a lot of patience. On the night of December 7th, the skies were unusually clear, no moon, low humidity, perfect seeing conditions. Matteo, like thousands of other observers around the world, had been tracking 3I Atlas since October. It had become something of a quiet obsession for many in the amateur astronomy community, not just because it was an interstellar object, but because it kept doing things that defied simple explanations. Strange pulses, sunward jets, flashes that didn't align with any known debris. But nothing Matteo had captured before prepared him for what appeared on his screen at 3:14 a.m. local time. The exposure wasn't long, just 60 seconds, but when he calibrated the image, the structure of the object startled him. It wasn't blurry, it wasn't chaotic, it wasn't even soft-edged like most comet nuclei appear, even through a well-tuned scope. Instead, what he saw was sharp, defined. A brilliant white oval, not round but elongated, with a symmetrical glow wrapping around it like an envelope of light. The glow wasn't even. It bent slightly, like a magnetic arc. And at the object's core, the brightness concentrated into a tight central band, something rarely captured in backyard observations. Matteo assumed it was a processing error, maybe a stacking glitch, or a misalignment in the field rotation. But after checking his frames one by one, the pattern held. Frame after frame, the object maintained its structure, not a smudge, not a distortion, a structure. He uploaded the image to a small forum of advanced amateur astrophotographers. It was picked up within the hour by a retired physicist in France, then reposted to a larger amateur community on an astronomy Discord server. The reaction was immediate and polarizing. Some accused Matteo of falsifying the data, injecting overlays, overprocessing, exaggerating contrast. Others ran the original FITS files through their own software and confirmed the same thing. It was real. What shocked everyone wasn't just the clarity, it was the geometry. Comets aren't supposed to look like this. Their cores are supposed to blur. Their comas are supposed to shift, distort, and stretch under solar radiation. But this image showed something symmetrical, something stable, something that, for a moment, didn't look like a comet at all. And then, within 48 hours, something even stranger happened. Other observers, from Finland, South Africa, Brazil, reported near-identical structures appearing in their captures of 3I Atlas. The structure was seen again and again, slightly rotated depending on the observation angle, but unmistakably consistent. This wasn't artifact. It wasn't software noise. It was part of the object. The forums lit up. Someone jokingly asked if Matteo had just photographed the engine housing of an alien probe. Another called it the cleanest interstellar geometry we've ever seen. But underneath the humour was a genuine unease. Because if this wasn't artificial, then it was natural. And if it was natural, then it was something we'd never seen before. NASA didn't issue a statement. Neither did ESA or JPL. But quietly, the coordinates from Matteo's session began appearing in back-end observation scheduling databases. Telescopes that had previously moved on from 3I Atlas were suddenly pivoting back. What started as a hobby image from a Spanish hillside had just rewritten the next chapter of observation, because once you see shape where there should be blur, you can't unsee it. When professional astronomers first reviewed the amateur images of 3i Atlas from December 7th, many expected visual noise, the kind that comes from backyard telescopes operating on the edge of their limits. But what they found wasn't noise, it was a pattern, and not just any pattern, symmetry. Symmetry in astronomy almost always means something deliberate. In stars, it suggests equilibrium. In galaxies, it hints at structural harmony shaped by gravity. But in comets, especially interstellar ones, symmetry isn't supposed to exist. These are chaotic objects, ragged composites of ice and rock, fractured by radiation, torn by thermal shock, and misshaped by millions of years tumbling through deep space. Yet the image from Spain, and later confirmed by observers in Finland and Argentina, showed something no known comet ever has, matching arcs on opposite sides of the central body, one curve on the left, one curve on the right, both equidistant from the nucleus, both glowing with a consistent brightness gradient that faded smoothly into the dark. The symmetry wasn't exact, nature never is, but it was close enough to trigger disbelief. Initial thoughts focused on optical illusions. Could it be diffraction, a lensing artifact from the telescope optics? But the same symmetry showed up across different instruments, different cameras, different software stacks, and most importantly, different latitudes. This ruled out hardware error. This was in the object. Scientists turned to morphology models. Could dust jets, emerging from rotational points, create mirrored arcs under the right conditions? Perhaps. But simulations quickly ran into trouble. The solar radiation pressure would disturb the symmetry within minutes. The coma would blur, elongate, and destabilize. There was no known scenario in which symmetrical arcs could hold shape for more than a few hours, let alone across multiple orbits and observation angles. More confusing was the motion. The arcs didn't move. Normally, as a comet rotates, any visible structures in the coma shift. Brightness slides across the surface. Jets appear to wobble. But in the December 8th data, the symmetrical features held their position. It was as if they weren't gas flows, but structures. Static, consistent, and unreactive to spin. Some theorists proposed a rotating binary core, a pair of small objects orbiting each other, creating symmetrical dust emissions. That would explain the arcs, perhaps, but not the lack of thermal fluctuation. Others suggested a flat reflective surface, spinning just slowly enough to project arcs into the glow. But again, the reflectivity gradient didn't match known materials, and the object's brightness curve didn't support a large flat geometry. As the images circulated, one term kept surfacing in private research groups: engineered symmetry, a pattern that doesn't emerge randomly, but by design. That concept remains controversial, even forbidden in some circles. But behind closed doors, physicists were running simulations that ignored the standard assumptions. Instead of modelling gas expansion, they modelled resonance. Instead of chaotic fragmentation, they modelled structural coherence. And strangely, those models fit. They didn't prove anything, but they held together longer than the traditional comet models. The arcs behaved more like magnetic fields than outgassed particles, more like hulls than halos. And once that idea crept in, it became difficult to unsee. No one wanted to publish first. Peer review demands caution, especially when the implications reach beyond physics. But the data didn't lie. The images were consistent. The symmetry was real. And most importantly, it wasn't fading. For days after December 8th, high-altitude infrared telescopes tracked 3i Atlas under near-perfect atmospheric conditions, and in each composite the arcs remained. Cool, even-toned, perfectly curved. Whatever this is, it's not breaking apart, it's holding shape. And in space, shape means something. When scientists describe a comet's brightness, they're not just talking about how shiny it looks. They're describing its albedo, the fraction of sunlight that reflects off its surface and into our telescopes. Most comets, especially those with active comas, have low albedo values. Their surfaces are dark, like soot. This is expected. Over time, solar radiation bakes away the bright ices, leaving behind carbon-rich crusts that absorb light instead of reflecting it. But the readings from 3i Atlas on December 8th don't follow that script. Not even close. Data collected across multiple instruments, from amateur CCD rigs to high-orbit telescopes, showed a sudden and sustained spike in reflectivity. Not just a brightening, which can happen as outgassing increases, but a sharp jump in albedo that could not be explained by increased dust or gas output. The central object, the nucleus, appeared to double its reflectivity in just over 6 hours, and then it held that level. That's not supposed to happen. In a typical comet, sudden brightening is caused by an outburst, a pocket of volatile gas explosively escaping and scattering sunlight. But outbursts leave signs, dust trails, Coma expansion, shifts in infrared heat signatures. None of those happened here. In fact, the Coma remained oddly stable, and the heat readings from ESA's solar orbiter didn't rise with the brightness. Instead, the light seemed to change without heat. That's not thermal emission, that's surface reflection. And this is where things get strange. When researchers looked at the light curves, the graphs that show how brightness changes over time, they noticed something unexpected. The reflectivity increase wasn't diffuse. It came from a specific angular sector on the object's sunward side. It was as if one portion of 3i Atlas had suddenly become mirror-like, bouncing sunlight at a higher rate than the surrounding material. This region wasn't just brighter. It was spectrally consistent, meaning the colour of the light matched what you'd expect from direct solar reflection, not from dust scattering, which tends to shift toward the red end of the spectrum. In simpler terms, this wasn't ice glowing. This was something bouncing light like polished material. Of course, scientists first searched for natural explanations. Could it be a layer of freshly exposed ice, more reflective than the crust it replaced? Possibly. But ice that bright would need to be nearly pure, and pure water ice sublimates quickly under solar heating. It wouldn't persist for more than a few hours, let alone stabilize across multiple orbits. Others proposed a coating of carbon dioxide frost, but even CO2 ice, while highly reflective under certain angles, sublimates at far lower temperatures. The temperature readings from the December 8th pass simply didn't match that behavior. Then came the angle analysis. The reflected light wasn't bouncing randomly. It peaked at a specific phase angle, the angle between the sun, the object, and the observer. That peak occurred at nearly the same value across 3 different observation points, suggesting the surface wasn't scattering light evenly. It was behaving like a flat or curved reflective surface, not like a dust-covered body. This brings up the term many scientists are reluctant to use, specular reflection. It's the kind of light you get from mirrors, metals, and polished surfaces. You don't get it from porous comet crusts. And yet, that's exactly what the December 8th data implied. The object was not glowing. It was gleaming. No one's claiming this proves 3i Atlas is artificial. But when an interstellar body defies the known albedo range of natural comets, holds reflectivity across hours of solar exposure, and returns spectral signatures that resemble engineered materials more than ice, you have to ask a harder question. What kind of surface reflects like this? And more importantly, why now? On December 8th, astronomers began to notice something that didn't quite make sense. It wasn't the brightness itself that raised concern. Comets fluctuate all the time. It was the rhythm, a subtle, repeating fluctuation in the glow surrounding 3i Atlas. It wasn't chaotic like most outgassing patterns. It wasn't random noise in the light curve. It was timed, predictable. And by all conventional physics, it shouldn't have been there. The first to observe it was a graduate researcher at the Mount Lemmon Sky Center in Arizona, reviewing high-cadence photometric data. The initial assumption was a calibration error. The brightness dipped, then rose, slightly but consistently, every 48 minutes. A mechanical vibration? An error in the telescope's timing software? But when the same rhythmic pattern appeared in backup logs from a separate facility in South Korea, it was clear. The signal was real. 3i Atlas wasn't just glowing, it was pulsing. The next question was obvious. What's causing it? In natural comet behavior, glow variations are driven by solar heating. As the nucleus rotates, volatile pockets are exposed, triggering jets and thermal changes. But that's a messy, delayed process. Gas takes time to sublimate. Heat takes time to radiate. There are lags, long ones, between solar input and optical response. What 3i Atlas showed wasn't a lag, it was a cycle, and it didn't correlate with the object's rotational period either. The known spin rate of 3i Atlas, determined by previous light curve modelling, was measured at roughly 9.6 hours. This was a fraction of that, so either the object had changed its spin dramatically, or this wasn't rotational at all. The glow pulsed outward from the nucleus, visible in ultraviolet and near-infrared bands. It appeared first at the centre, then diffused through the coma. Each pulse began with a brief brightening, peaked quickly, then decayed with mathematical smoothness, like a waveform. It wasn't jagged, it wasn't irregular. It followed a clean sinusoidal curve. Telescopes in Chile and Japan confirmed the effect. When they overlaid the readings from 5 separate facilities across 3 continents, the phase timing matched to within a margin of 0.4 seconds. The glow wasn't responding to local atmospheric conditions. It wasn't observational error. It was systemic. It was internal. At this point, some began to wonder whether the pulses were thermal, perhaps a kind of periodic venting, where gas built up under pressure and escaped rhythmically. But spectrographs showed no accompanying spikes in carbon monoxide, water vapour or hydroxyl radicals. The emissions stayed flat. The only thing changing was the light. A few researchers quietly raised another possibility: modulation. In electronics, modulation is when a carrier signal is altered in amplitude, frequency or phase to encode information. That's not something you expect to apply to comets, and no one seriously claimed this was communication. But the structure of the pulse, the way it maintained amplitude and phase across different viewing angles, hinted at something controlled. At a minimum, it suggested regulation. This opened the door to one of the more disturbing implications. What if the pulses weren't just light, but a byproduct of internal systems? In spacecraft engineering, energy redistribution and battery cycling can produce electromagnetic artifacts. Pulsed thermal venting is also a common method for regulating internal temperatures during prolonged solar exposure. Is that what we're seeing here? Or is this a natural mechanism we simply don't understand? One that has never appeared in any previously observed interstellar body? The glow faded back to baseline by the end of the day, but the pattern had already been established. The pulse was there, and whether it was natural, mechanical, or something else entirely, it was consistent. The universe is full of random light, but when light pulses with timing, with repetition, and with symmetry, it starts to look like something else. It starts to look like a system. Doppler shift is one of the most reliable tools in astronomy. When an object moves toward or away from a detector, its light shifts in frequency. It's the same principle that makes a passing ambulance change pitch as it moves past. But in space, this effect allows us to measure motion down to fractions of a meter per second. It's how we study exoplanets, binary stars, even distant galaxies. So when Doppler data from 3i Atlas started to drift, again, scientists took notice. This wasn't the first time it happened. A similar Doppler anomaly occurred back in late October, during the object's approach to perihelion. At the time, it was attributed to observational error, outgassing, or perhaps rotational asymmetry. But this time was different. The shift didn't correlate with any change in velocity. The trajectory of 3i Atlas remained stable. The drift was spectral, not mechanical. In the early morning of December 8th, the Canary radio array detected a soft, measurable redshift in the reflected radio signals bouncing off the object. It lasted just under 90 minutes, then reversed, shifting slightly blue, then returning to baseline. That's not consistent with forward motion. That's consistent with internal modulation. The wavelength change was subtle, barely distinguishable from background noise, but 3 separate observatories recorded the same curve. It followed the same rhythm as the light pulses seen the day before. 48-minute intervals, peaking at nearly the same moment the object's brightness surged. This raised a new set of questions. Could it be vibration? Could the object itself be oscillating on a structural level, creating micro-Doppler effects as different surfaces tilted toward and away from Earth? Possibly. But if so, those oscillations would likely show up in the photometric data as flickers or distortions in the coma. Nothing like that was present. The glow remained smooth. The tail stayed aligned. So what was drifting? Some scientists turned to thermal explanations. Perhaps the surface was expanding and contracting in response to sudden heating. a kind of solar-induced resonance, but the temperature data didn't support that either. Surface heat signatures were dropping, not rising. No thermal swell was occurring. The pattern instead resembled something seen in controlled environments, when electromagnetic interference skews returning signal frequency. The phenomenon, known as coherent backscatter, can occur when structured surfaces reflect energy with slight delay depending on material composition. It's rare in nature. It's more common in engineered reflectors. The magnitude of the drift also revealed something else. It was too clean to be random. Natural processes tend to leave noise in the data: wobble, irregularity, decay. This drift didn't decay. It returned to zero on a perfectly symmetrical slope, both in and out. That kind of symmetry is almost never seen in debris fields or cometary behavior. It suggests a system that regulates its own emissions. As always, astronomers resisted the urge to speculate too far. It could be a natural oscillation, something we've never observed before in interstellar comets. Perhaps some unknown material on the object's surface responds to solar radiation in ways our models can't yet explain. But one detail was harder to dismiss. The frequency drift matched the same rhythm as the photometric pulse. Two separate measurements, light and radio, showing synchronized fluctuation from different parts of the spectrum. That's not a coincidence. That's correlation. In the days that followed, several independent radio stations around the globe attempted to replicate the readings. Some failed, others succeeded. But the ones that did showed something even stranger. A narrow spectral notch just adjacent to the drift band. A gap. A silence. If it's natural, then we've just discovered a new form of spectral resonance. If it's not, then the object isn't just reflecting energy. It might be modulating it. And in space, modulation usually means control. It started as a thin spike, barely visible against the blur of the Coma, a narrow shaft of light extending sunward, captured in a long exposure image from the Cerro Tololo Inter-American Observatory in Chile. The initial assumption was a camera artifact, possibly a lens flare or a collimation streak. But then came a second image, and a third. Different filters, different detectors, different latitudes, all showing the same thing. The jet was back. This wasn't just any gas plume. It was narrow, collimated, and alarmingly stable, cutting directly into the solar vector like a filament of energy threading itself into the sun's magnetic field. Scientists had seen it once before, in late October, when 3I Atlas crossed its perihelion path. At the time, it was dismissed as a one-off event, a coincidental outburst, possibly triggered by volatile exposure or a rapid phase transition on the surface. But here it was again, and this time it had returned with structure. The jet didn't spray or fan like typical comet emissions. It didn't diffuse or shimmer with turbulence. It held shape. Over the course of several hours, the beam maintained its orientation with minimal deviation, even as the nucleus rotated and the Coma shifted slightly under changing solar wind conditions. That kind of stability defies what we know about natural jet mechanics. On most comets, jets form when sunlight heats localized patches of volatile ice near the surface. That ice sublimates and escapes through cracks or vents, forming jets that arc into space. These are usually chaotic, shifting, and pressure-sensitive. They bend, scatter, and flicker. But this jet remained pin-straight, laser-like, as if it was being directed. High-contrast imaging from the James Webb Space Telescope supported the claim. Its near-infrared composite showed a central emission channel no wider than a few dozen meters at the base, expanding only slightly as it stretched hundreds of kilometers outward. The emission intensity was consistent from origin to terminus. There were no signs of dispersion, lateral flow, or thermal instability. More curiously, the jet pointed not away from the sun, but directly toward it. That orientation violates the most basic rule of cometary physics. Solar heating should push volatile gas outward. Solar radiation pressure should shape jets anti-solar. But this structure ignored both forces. It was actively resisting solar drag. The jet was pressing against the sun, not fleeing from it. That raised a disturbing possibility: thrust. If 3I Atlas was emitting gas at high velocity in a sunward direction, then the reaction force would push it anti-sunward, precisely the kind of controlled acceleration theorized during its post-perihelion deviation. Could this jet be a propulsion mechanism? Was it active now, months after its closest solar pass, spectral readings added more questions. Unlike water or carbon dioxide plumes, this jet didn't show the typical chemical signatures. It lacked hydroxyl radiation, carbon monoxide bands, or sodium tail markers. Instead, it glowed faintly in a narrow band of infrared, associated with ionized carbon, a component more common in engineered plasmas than natural comet tails. Some scientists suggested the jet might be electromagnetic in nature, a kind of collimated ion stream, like those used in Hall effect thrusters aboard satellites. But to generate a plume like that, you'd need a stable voltage source, a power system, a containment structure, all things that, in theory, don't exist on comets, and yet the jet remained. Over the next 10 hours, the structure faded slowly, not with a pop, but with a taper, as if the emission had been throttled down or deliberately stopped. It didn't sputter, it didn't fracture, it simply narrowed and vanished. That's not behaviour, that's operation, and if this object is operating even in the simplest way and rejecting material in a directed, regulated fashion, then we may need to stop calling it a comet altogether. Because comets don't have direction, they don't have structure, and they certainly don't have jets that turn back on. Infrared data is the quiet language of space. It tells us things the visible spectrum can't. It reveals heat, composition, surface texture, and chemical transitions. It's how we detect the signatures of water, carbon dioxide, ammonia, and organic molecules on comets. It's how we spot exoplanets hiding behind stars. And in the case of 3I Atlas, it just told us that something is missing. On the morning of December 8th, the James Webb Space Telescope completed a scheduled narrowband infrared sweep of 3I Atlas. Using its mid-infrared instrument, MIRI, the telescope scanned across a wide range of wavelengths, each chosen to probe specific materials: silicates, ice crystals, volatile gases, and organic dust. These kinds of passes are routine. The data is usually dense. Every pixel glows with a dozen possible chemical fingerprints. But this time, there was a silence. A stretch of infrared frequencies, centered between 10 and 12 microns, returned almost no signal. Not faint, not degraded, absent. It was as if something in that band had been erased. This shouldn't be possible. Even the darkest natural surfaces emit thermal radiation. A chunk of rock drifting through space, warmed even slightly by the sun, will glow in the mid-infrared. So will gas clouds, icy grains, or even thin dust layers. In fact, most. Comets have strong emissions in this exact band, particularly from carbon dioxide and silicate dust. The 10 to 12 micron window is a known hotspot for detecting heat-based chemical activity. But 3I Atlas didn't emit anything. It showed a spectral void. At first, scientists considered an equipment fault, maybe a dead detector pixel, maybe a misaligned filter. But cross-checks with backup instruments ruled that out. The telescope was functioning perfectly. It was seeing background radiation from distant stars just fine. But when its sensors locked onto 3I Atlas, that band went dark. This raised two possibilities, both difficult to accept. The first, absorption. That would mean 3I Atlas is coated in a material that selectively absorbs radiation in that band. Such materials exist on Earth, engineered carbon composites, and infrared black ceramics used in aerospace and military shielding. But in nature, there's nothing known that behaves this way across such a narrow and precise frequency range. It's not how ice or dust behaves, and it's certainly not how carbon dioxide emits. The second, cancellation. This would imply that the object is emitting infrared in that range, but in a pattern that cancels itself out, possibly through destructive interference or phase-matched emission. This concept borders on engineered optics. It requires a level of control over emission patterns that no natural object has ever demonstrated. Either way, the result was the same, a comet that doesn't radiate where it should. This anomaly becomes even more significant when viewed alongside the object's increasing reflectivity. Normally, high albedo surfaces reflect visible light and radiate strongly in the infrared, but 3I Atlas seems to be doing the opposite, glowing in specific bands, while going completely dark in others. That suggests selective emission. That suggests control. Some scientists have proposed exotic dust coatings, possibly formed in another star system, that contain unknown minerals or compounds. Others suggest microcrystalline structures that filter outgoing radiation like a tuned surface lattice. But none of these theories explain how a naturally formed comet could maintain such spectral discipline over time, across multiple rotation cycles and under variable solar exposure. Infrared isn't just light, it's heat, it's entropy, it's what the universe does when it's done doing things. But here, the heat didn't show up, the energy didn't escape, the silence wasn't noise, it was data. And when something in space chooses not to emit, not randomly, but precisely, it tells us it's not just reacting to physics, it's managing it. In space, cooling is a luxury most objects don't get. Everything exposed to the sun, even briefly, soaks up energy. Ice melts, dust heats, rocks glow. Whether it's a planet, a satellite, or a simple chunk of cometary ice, the rules are universal. Proximity to a heat source means temperature rises and objects either radiate that heat away or slowly build it up. Especially for a body moving inward through the solar system, cooling is the last thing you expect. But 3i Atlas isn't following expectations. Thermal sensors aboard ESA's solar orbiter and ground-based infrared telescopes in Hawaii registered something strange beginning late December 7th. Across a full 12-hour observation window, 3i Atlas's surface temperature declined. Not slightly, significantly. The drop was measured at over 7 Kelvin, enough to push the body's thermal profile below that of comets in similar solar orbits. At 1.6 astronomical units from the Sun, the object should have been warming gradually. Instead, it was cooling fast. This wasn't a processing error. Independent teams reran the thermal curves using radiometric data from multiple instruments. Different sensors, different angles, different atmospheric conditions. The trend was consistent across the board. 3i Atlas was shedding heat, and more curiously, it was doing so without any visible increase in Coma activity or gas venting. That alone made no sense. In cometary physics, cooling often results from sublimation. As ices turn into gas, they take thermal energy with them. But that process leaves behind evidence: a growing coma, jets of vapour, or spikes in hydroxyl emissions. None of that was observed. The coma remained stable. Jet structures didn't change, and the infrared spectral bands typically associated with evaporating ice stayed flat. So where was the energy going? One early theory suggested surface shadowing. Perhaps a rotation brought darker, less reflective regions into view, reducing absorbed sunlight. But that doesn't explain the magnitude of the drop. A 7 Kelvin shift requires a major loss of heat, not just lower exposure. Another possibility was radiative emission. Perhaps the object had been storing thermal energy internally and suddenly released it. But again, radiative emission shows up as a spike in infrared brightness. That spike didn't appear. In fact, certain bands had gone missing entirely just hours earlier. That led some scientists to propose something more radical: thermal regulation. In engineered spacecraft, heat isn't just a side effect. It's a factor that's carefully managed. Radiators open and close, insulation layers shift, energy is redistributed internally. Could 3i Atlas be doing something similar? The idea sounds absurd, unless you consider the object's behavior across the previous days. Controlled pulses of brightness, specular reflection in narrow optical bands, now a drop in thermal signature without any mechanical cause. The pieces don't fit into a simple natural model, but they align uncomfortably well with system behavior. Adding to the mystery, the cooling occurred during a period of increased solar flux. The Sun had just ejected a mild coronal mass ejection, and solar wind activity was elevated. Every other object in its path, satellites, planetary surfaces, even solar sails in distant orbit, showed minor heating effects. 3i Atlas did the opposite. Some researchers proposed an electromagnetic shielding effect, a conductive surface dissipating solar energy before it could be absorbed. That might explain the infrared silence. It might even account for some of the reflectivity spikes. But it requires the kind of surface chemistry not seen in natural ice and rock compositions. It requires exotic materials, possibly metals, possibly carbon structures we don't yet understand, or materials we've never encountered because they weren't formed here at all. Cooling in space is rare. Passive cooling under active solar radiation is unheard of. But that's exactly what 3i Atlas is doing. It isn't overheating, it's stabilizing, and in the language of systems engineering, that's not failure, that's control. In comet science, the word antitail is a bit of a misnomer. Despite the name, it isn't truly a tail in the classical sense. It's not a stream of particles flowing backward into the solar wind. Instead, it's a perspective illusion, dust particles released earlier in the comet's orbit, lingering along its orbital plane and momentarily appearing to form a sunward-facing spike when Earth's line of sight aligns just right. Most antitails are fleeting. They appear for a few days, then dissolve as geometry shifts. They're beautiful but brief, and above all, they're passive, just lingering trails of old dust lit by sunlight and shaped by the laws of orbital mechanics. But 3i Atlas has broken that pattern completely. On December 8th, new high-resolution composites from observatories in Chile, Australia and La Palma confirmed what many amateur astronomers had already begun to whisper. The antitail is still there, still sharp, still sun-facing, and still growing. This is not normal. By this point in its trajectory, 3i Atlas should have passed the orbital angle that makes antitails visible. Earth has shifted its position. The geometry has changed. The dust that once aligned should now scatter behind it. And yet, the sunward spike persists, not fading, not dissipating, but remaining as crisp and coherent as it was 2 weeks ago. Even more striking is the structure. Instead of appearing diffuse or curved, the antitail now forms a narrow band, like a filament. It stretches directly toward the sun, cutting across the coma like a laser etched into the dark. And unlike the primary tail, which bends slightly under solar wind pressure, the antitail holds its line. This behavior is physically impossible under traditional models. Natural dust particles respond to radiation pressure. They drift. They scatter. They do not form coherent lines that defy distance and time, and they certainly don't stretch forward into the solar wind unless something is actively forcing them to do so. At first, researchers considered a complex geometric illusion. Perhaps Earth's motion and the object's orientation had coincidentally realigned the orbital dust plane. But orbital simulation software showed no such window. The Earth object-Sun angle was well past the expected antitail phase. By any model, the effect should have faded. It hasn't. So what are we looking at? One hypothesis, difficult to accept but impossible to ignore, is that the antitail isn't a passive trail at all, that it's an active stream, a directed emission of fine particles or gas being ejected toward the sun. And if that's true, the implications are staggering. Comets don't push material sunward. The solar wind doesn't allow it. The pressure gradient always forces particles away from the sun. The only way to push back is through propulsion, through a mechanism that forces matter to flow against the dominant force field. In other words, thrust. If 3i Atlas is generating a sun-facing outflow, then it's not just surviving solar pressure, it's countering it. Spectral data adds another layer. Instruments scanning the antitail region detected unusually high coherence in particle sizes, primarily micron-scale grains, distributed with minimal variance. That kind of uniformity doesn't arise from random shedding. It implies selection, curation, possibly filtration, or possibly control. The composition also matters. Preliminary readings indicate a higher carbon-to-silicate ratio in the antitail than in the main coma. That suggests the material being ejected forward is different, chemically distinct, from the rest of the object. It's not remnant dust, it's something else, something new. Even conservative scientists are beginning to shift language. What was once called the antitail is now appearing in technical memos as sunward-directed structure. A subtle change, but one that speaks volumes. The language of passive illusion is being replaced by the language of mechanics, because what we're watching might not be perspective, it might be propulsion, and if that's the case, 3i Atlas isn't just defying distance, it's choosing direction. Every active comet wears a kind of atmospheric veil, a loose, glowing cloud called the Coma. It's formed when sunlight heats the nucleus, causing volatile ices to sublimate and release gas and dust. That expanding material surrounds the solid core, forming a diffuse, shimmering halo that can stretch for thousands of kilometers. It's a dynamic feature, but one governed by simple physics. More heat, more outgassing, more coma. Less heat, less coma. That's why what happened on December 8th has left scientists struggling for words. Images from Cerro Paranal in Chile, taken during a 6-hour high-resolution observation session, revealed something never before documented in any known cometary object. A sudden, rapid collapse of the coma. Not gradual, not fragmented, but a coordinated contraction of the cloud. The outer glow tightened inward. The visible gas and dust seemed to retreat, as if being pulled back toward the nucleus. For nearly 90 minutes, 3i Atlas appeared stripped, bare, even, its previously broad coma reduced to a thin, compressed layer just above the surface. It wasn't faint, it was focused. The light didn't vanish, it reorganized. And then, just as abruptly as it began, the coma returned. Within the next observational cycle, the halo expanded again, regaining its previous size and luminosity, almost perfectly. But the gradient had changed. The outer layers were sharper, the glow was more even. There was less distortion in the surrounding dust envelope. It looked cleaner. This wasn't fragmentation, it wasn't fading, it was behavior. Naturally, researchers began scrambling for explanations. The first thought was a sudden drop in solar wind pressure. Maybe a temporary lull in the environment caused the outgassed particles to collapse inward. But the Solar Dynamics Observatory showed no such dip in heliospheric conditions. In fact, solar wind levels were rising at that time due to an approaching coronal mass ejection. The timing made no sense. Another theory. A sudden vent closure. Perhaps internal pressure shifted, choking the primary gas release and halting outflow. But this would normally be chaotic. In known comets, such events trigger fragmentation, wobble, or asymmetrical jet activity. But 3i Atlas showed none of that. It held shape. It remained balanced. No spin drift, no jets. Just a calm, organized glow. A more exotic possibility entered discussion. Electromagnetic interaction. Some researchers floated the idea that 3i Atlas was briefly reacting to a change in the solar magnetic field. If the coma particles were charged, or partially ionized, a localized magnetic fluctuation might cause them to collapse toward the nucleus along field lines, like iron filings around a magnet. But again, the collapse was too symmetrical, too centered. In fact, the symmetry is what bothered people most. In natural cometry physics, collapses are chaotic, jagged, messy. This wasn't. The entire coma contracted evenly, not like an explosion, but like a breathing motion, and when it expanded again, the result looked more precise than before, as if something had reset it. This led to one of the more controversial suggestions: active field control. Some forms of spacecraft design propose using weak magnetic containment fields to shape dust plumes or ionized gases, not to hold them indefinitely, but to redirect or refine their paths, to maintain stability during volatile operations. Could that be what we're seeing? Is 3i Atlas regulating its outer material? There's no direct evidence of artificial field generation, no signature pulses, no strong emissions, but the motion of the coma, first collapsing, then blooming, matches what you'd expect from a pulsed containment release. Not constant, not sustained, but timed. Something interrupted the coma. Something pulled it back, held it, and then let it go. And that something, whatever it is, didn't break the object. It made it sharper. Comets fracture. That's what they do. When ice meets sunlight, when internal gases heat and expand, when gravity from planets or tidal forces twist their structure, they break. Sometimes in halves, sometimes in dozens of fragments. Comet Linear did it. So did Elenin. Even the mighty comet Shoemaker-Levy 9 shattered into pieces before slamming into Jupiter. So when 3i Atlas began experiencing measurable stress, from solar radiation, from changing acceleration vectors, from sudden outgassing pulses, everyone braced for the signs: stress cracks, trailing debris, plume disintegration, rotation instability. But nothing broke. On December 8th, astronomers observed the object during one of its most thermally volatile moments, a brief window just after perihelion exposure when surface materials would be expected to shift, fracture, and release built-up pressure. Temperatures across the surface had fluctuated dramatically, and according to standard cometry models, the risk of fragmentation would have been at its peak. Instead, 3i Atlas held together, not just structurally, but cleanly. No trailing shards, no spin-up, no loss of mass outside its regular coma profile. Spectral scatter plots from Lucilla Observatory showed no increase in small particle diffusion. Hubble's wide-angle scans detected no new motion blur distortions, and perhaps most surprising, LIDAR tracking from the Lunar Pathfinder relay confirmed that the object's dimensions remained stable to within less than 1%. If this was a comet under stress, it was enduring it like nothing we've seen before. Some researchers speculated that we had simply missed the fragmentation, that a piece may have broken off and immediately disintegrated. But the Coma's brightness curve remained consistent, and the mass loss wasn't significant enough to hide a missing chunk. Others wondered if the object was made of denser material, perhaps more metallic or fused rock than volatile ice, but previous observations already confirmed sublimation signatures and dust ejecta consistent with standard comet chemistry. That left one hypothesis: internal cohesion. Something about the structure of 3I Atlas was resisting the internal expansion forces that would normally tear an object apart. Maybe it had internal voids that absorbed pressure, or maybe its outer shell had restructured to manage thermal gradients. But then came a deeper problem. Stress didn't just fail to break the object, it seemed to be distributed. Magnetometer data from the Parker Solar Probe revealed something strange in the plasma environment around the object. Microfluctuations in the local magnetic field that hinted at a patterned interaction, as if 3I Atlas was shedding stress in controlled bursts, possibly through pulsed jet activity or electromagnetic discharge. These weren't wild, chaotic ejections. They were timed, subtle, balanced, and they never destabilized the body. That's not how natural comets work. That's how engineered structures behave under load. Spacecraft, for instance, are designed to breathe, to flex under heat stress, to vent pressure through microvalves, to redistribute thermal energy before it builds into failure. Could 3I Atlas be doing something similar? Is its resilience the result of composition or of design? We don't know. But the longer it travels, the less it behaves like something barely holding itself together. It's not cracking, it's not shedding, it's not tumbling into chaos like every other stressed interstellar visitor we've ever seen. Instead, it's adapting, it's holding, and that's forcing scientists to reevaluate something once considered obvious. If it doesn't break under pressure, was it ever meant to? Solar wind doesn't ask for permission, it doesn't negotiate, it moves, and everything in its path reacts. Comets, especially, are shaped by it. Their tails are sculpted by the relentless stream of charged particles blowing outward from the sun. The solar wind pushes gases, ionizes them, and forms long, sweeping ion tails that always point away from the sun, regardless of the comet's direction of motion. That's how we know what's natural. The tail runs from source to solar escape, cause and effect, perfectly aligned. Until now. On the morning of December 8th, deep field scans from the Solar Terrestrial Relations Observatory, Stereo B, picked up something subtle but deeply unnerving. The solar wind was still flowing, but Thrus Atlas was no longer reacting the way it should. Instead of forming a clean, oppositional tail, the object's ion stream appeared disrupted. Not frayed, not dissipated. Reversed. The outer particles that had previously flowed neatly away from the sun were now forming a soft curve, a bend in the structure that tilted sunward, then looped back. This arc didn't match any orbital movement. It didn't follow momentum. It looked like a field redirection, as if the particles were being guided. That's when plasma monitors aboard the AC spacecraft confirmed a more startling detail. The magnetic signature of the solar wind was clean. There had been no coronal mass ejection, no flux rope, no directional shift. The solar wind didn't change. 3I Atlas did. Its interaction with the wind had flipped. What was once repelled now seemed, somehow, redirected. The ion tail, instead of fleeing from the solar wind, appeared to be responding to a field of influence around the object. A magnetic bubble, perhaps, or a kind of repulsor boundary. Either way, the object wasn't passively being pushed anymore, it was shaping the flow. Veteran heliophysicists were quick to point out how rare this is. In Earth's orbit, artificial satellites with active magnetic shielding can bend solar particles. Larger planets like Jupiter and Saturn have their own magnetospheres that warp the incoming wind. But a comet isn't supposed to do this. Even stranger, the reversal was periodic. Over the span of 6 hours, the tail structure oscillated, first aligned to the classic solar model, then bent, then briefly collapsed into a halo, then reformed again, this time wider, more diffuse. It looked coordinated, not random. This kind of behavior would typically demand either an internal magnetic dynamo or some form of plasma sheath, mechanisms never associated with small, icy bodies. But data from ground-based radio telescopes suggested something active at play. Emissions consistent with low-frequency plasma oscillations. Quiet, but regular. It wasn't just the direction of the tail that changed. The energy density within it dropped, even as solar wind intensity increased. That implied active mitigation, like pressure was being bled off before it could shape the material. Think of a sail that suddenly folds in the wind, not because the wind stopped blowing, but because the sail decided to furl itself. NASA didn't release a public statement, but buried in a routine space weather bulletin was a phrase not seen in previous 3i Atlas logs. Field Interactive Response Zone. What that means exactly hasn't been defined, but in plain language it means this. 3i Atlas isn't just reacting to the solar wind anymore, it's negotiating with it. Some even speculate the object is using the wind to maneuver, not resisting it, but riding it. Like a surfer shaping their board, subtly shifting balance with every pulse. If that's the case, then 3i Atlas isn't being pushed through space, it's navigating. Most comets are messy mirrors. Their surfaces are irregular, they're outgassing chaotic, they're spinning unpredictable. As they tumble through space, the sunlight they reflect scatters unevenly, producing a light curve that's jittery, diffuse, and, most importantly, random. Astronomers know this pattern well. A standard comet's photometric signature flickers in response to its rotation, jet activity, and varying surface reflectivity. It's a natural, noisy signal. And that's what researchers expected from 3i Atlas, especially as it approached its closest point to the Sun. But on December 8th, something changed. The light it was giving off stopped behaving like light from a comet. At 3:12 UTC, a string of near-infrared photometers spread across Chile, Hawaii, and Japan registered a harmonic reflection pattern, a clean rhythm in brightness that repeated with a near-perfect interval of just under 4 minutes. This wasn't a flare, it wasn't a spin wobble, it was a pulse, even more unsettling. It remained consistent for almost 12 hours. Astronomers tried to brush it off as a surface anomaly. Perhaps one region of the object had become unusually reflective, rotating into view at just the right angle to catch sunlight in a repeatable pattern. But the geometry didn't work. The brightness didn't fall off as it should have. It stayed strong, symmetrical, centered. Then came the polarization readings. Using data from the European Southern Observatory's high-sensitivity polarimeter, scientists observed that the reflected light from 3i Atlas was polarized in a way that strongly suggested organized structure, not particulate scattering, not randomness, but planes of reflection, as though the light were bouncing off something flat, angled, and consistent. This completely breaks the model, because natural comet surfaces aren't flat, they're chaotic, porous, uneven, composed of mixed materials that scatter light every which way. For a polarized reflection of this clarity to exist, the surface, or at least part of it, would have to be smooth and structured, perhaps even artificial. Worse still, the reflected light didn't shift even as the solar incidence angle changed. The Sun moved, Earth rotated, and yet the angle of polarization held steady for a window that defies any known rotational mechanics. This implies something is tracking the light source, or adjusting its surface to maintain the beam. At this point, the explanation started to stretch. Some suggested a frozen lake bed, a large glassy sheet of ice that just happened to be aligned correctly. Others proposed a silica-rich region polished by previous outbursts. But the consistency and duration of the reflection broke those models. Ice sublimates, dust shifts, nothing stays perfect under solar heat. Still, the reflection held. And there's one more twist. Spectral analysis of the reflected light showed an unexpected absorption dip, a faint but recurring signature, at a wavelength associated with engineered composite coatings. Not natural minerals, not carbon dust. Something closer to the materials used in satellite shielding. That discovery wasn't included in any public releases. It showed up buried in the raw datasets, but those who know how to read the data caught it. And now, the whispers are growing louder. This isn't just bright, it's controlled. The rhythm, the consistency, the polarization, the possible coatings. Taken individually, they might be anomalies, Taken together, they point to something more organized, something that reflects not by chance, but by choice. 3i Atlas isn't just lit by the sun, it may be using light, and in the silence of space, reflection isn't always passive. Sometimes it's communication. In the physics of space travel, natural or engineered, acceleration leaves a trail. For comets, this trail is literal. As they speed through the inner solar system, ice turns to gas, dust lifts from the surface, and solar radiation pressure stretches all of it into a tail. And that tail should always tell the truth. When a comet changes speed, the length, shape, and direction of its tail shifts accordingly. Push it harder, and the tail gets longer. Nudge it sideways, and the tail bends. The faster the acceleration, the sharper the distortion in the dust plume behind it. The tail becomes a record of motion, a visual echo of the forces at play. That's why what scientists saw on December 8th has left so many of them silent, because 3i Atlas changed velocity, and its tail didn't flinch. It was first noticed by a team at the Mount Lemmon survey, which had been tracking the object's position against background stars using high-precision astrometry. Their early morning readings showed something strange. The object had shifted slightly off its projected path. Not by much, just enough to register. A few arc-seconds of discrepancy, spread across a couple of hours. But the math didn't lie. The object had accelerated, not drifted, not coasted, accelerated. Yet the tail looked untouched. Images from the Pan-STARRS Observatory confirmed the same thing. There was no tail flare, no directional distortion, no extra broadening in the dust spread. The plume behind 3i Atlas remained narrow, elegant, and perfectly centered. A frozen line of symmetry, as if the object hadn't moved at all. But it had, and that broke every model of natural propulsion. Dust plumes react. They're incredibly sensitive to change. Even slight pressure shifts can shear off edges or create forks in the tail. When comets accelerate, whether by sublimation outburst or gravitational pull, their tails betray the motion instantly. But 3i Atlas showed none of that. So scientists tried to work backward. Maybe the acceleration was optical, a glitch in the parallax from Earth's rotation, or from thermal interference in the instruments. But multiple sites on different continents, under different atmospheric conditions, recorded the exact same shift. Next theory. Maybe the dust tail is being bound by electric charge. In some exotic cases, if particles become ionized and the object emits a weak magnetic field, the tail can appear narrower than it should. But that wouldn't explain the core issue. The tail stayed aligned even as the body accelerated. The tail didn't lag. It followed instantly, as if it were part of the object itself. The idea that emerged next was difficult to say aloud, even in private research groups. What if the tail isn't a tail? What if that long, luminous streak we've been calling a dust plume is something else entirely? A controlled emission, an engineered signature, a kind of navigational marker that doesn't respond to physical forces because it's being projected. In other words, what if the tail isn't a consequence of movement, but a decoy of stillness? It's an unsettling possibility and there's no solid proof. But the facts remain. The object changed speed, the tail did not, and the only things we know of that can alter velocity without disturbing their visual wake are spacecraft, or at the very least things designed to hide their motion. And in that case, the tail isn't a message of where it's been. It's a mask for where it's going. Mass is one of the hardest things to measure in space, especially when you're watching an object that doesn't behave the way it's supposed to. When a comet enters the inner solar system, scientists can estimate its mass using a combination of indirect observations, its velocity, its light curve, the intensity of outgassing, and how it reacts to gravitational influences from nearby planets. It's never perfect, but over time, as more data accumulates, a reliable mass estimate emerges. With 3i Atlas, that number keeps changing, and not in the direction anyone expected. Initial estimates taken from its first observable arc earlier in the year placed it among the heavier class of interstellar visitors. Not quite as massive as Oumuamua was projected to be, but still significant. Enough to cause detectable gravitational perturbations. Enough to produce the kind of activity we were seeing in its Coma and tail. But since entering the inner solar system, the mass estimates have continued to drop. And on the morning of December 8th, they dropped again. This time, the numbers came from a triangulated data run involving NASA's Deep Space Network. ESA's Gaia orbital platform, and the Chinese Fast Radio Observatory. Each station used slightly different methods: gravitational lens tracking, inertial drift analysis, and reflected signal delay, but all pointed to the same unsettling conclusion. 3i Atlas is lighter than it should be. That might not sound alarming. Comets lose mass all the time as they shed gas and dust near the Sun. But here's the catch. 3i Atlas hasn't lost that much visible material. Its coma has remained stable. No significant fragmentation has occurred. And yet, the numbers keep dropping. Now by nearly a third compared to pre-perihelion estimates. Where is the mass going? Some scientists think it's hidden in a material form we can't detect. Maybe low reflectivity particles that have dispersed beyond the visible tail. Others wonder if the object is ejecting something directionally, in a way that evades standard observation, like focused gas vents that dissipate rapidly into the solar wind, invisible unless viewed from the exact right angle. But another theory is more chilling. What if the mass never existed to begin with? In other words, what if our initial estimates were wrong, not because of bad data, but because 3i Atlas was intentionally presenting itself as more massive than it actually is? This idea hinges on a disturbing but increasingly discussed possibility that 3i Atlas has a variable reflectivity profile. If the object is actively adjusting how it reflects light, or using materials that scatter energy in misleading ways, it could trick our instruments into reading it as larger and denser than it really is. Imagine a hollow object designed to look dense, or a reflective shell wrapped around something much smaller. The fact that its mass appears to shrink without shedding matter is a signal, maybe not of deception, but of design. A comet doesn't hide its own gravity. A natural object doesn't rewrite its optical density in real time. And there's one final data point that scientists can't ignore. During the same window that mass estimates dropped, the object's acceleration pattern became smoother, less jitter, more control, as if reducing mass allowed it to move more precisely, as if a lighter frame was never the byproduct, but the goal. If that's true, then we have to consider something few are willing to say outright. 3i Atlas isn't just moving through the solar system. It might be optimizing itself as it goes. There are flashes in space that come and go with reason. Solar flares, reflected glints from tumbling satellites, a momentary alignment between Earth, an object, and the Sun. All explainable, all predictable. But what happened again on December 8th wasn't a one-off anomaly, it was a repeat. And in science, repetition changes everything. At exactly 0441 UTC, observers from multiple ground-based stations, including 2 in Arizona and 1 in the Canary Islands, reported the sudden appearance of a sharp, narrow flash coming off 3i Atlas. It wasn't a broad flare, like you might get from a dust plume catching sunlight. It was fast, contained, and, according to photometric readouts, reflective in a way that defied explanation. It looked like a mirror. And it wasn't the first time. The first of these mirror-like events happened a week earlier. A sudden spike in luminosity that caught researchers off guard. At the time, they chalked it up to a coincidental angle, maybe a smooth patch of ice briefly aligned with Earth and bounced the sun's light directly at us. But when it happened again, at the same angle, and for nearly the same duration, that explanation began to unravel. What's most unusual is how tight the flash was. Normally even the most reflective patches of a comet's surface will scatter light diffusely, over a wide arc. But this flash was directional. It came from a narrow point spiked sharply, and then vanished. Instruments measured a return curve that dropped off in milliseconds. It didn't linger, it didn't fade, it cut off like a signal. That's not something we see in natural objects, that's something we see in engineered ones. Think of the way light reflects off a polished solar panel, or the glare off the window of a satellite when it rotates through sunlight. That's the kind of signature we're seeing, but from a comet, or something pretending to be one. The location of the flash was consistent with the specific quadrant on 3i Atlas, near its mid-body slightly trailing its direction of motion, and here's where it gets stranger. This is the same region that showed abnormal polarization patterns earlier in the week. In both events, the light wasn't just bright, it was ordered. Polarimetry readings suggest a single plane of reflection. Not fractured ice, not airborne dust. A surface, flat, reflective, and possibly reactive. And then there's the timing. Both flashes occurred at moments when the object was near solar alignment, a position where sunlight hits at a steep angle, and Earth's view is optimal for reflection. But here's the key. 3i Atlas didn't rotate in a way that would explain the alignment. Its orientation stayed stable, which means either the surface itself moved, or a structure emerged. A panel, a fin, an array, no one knows. But the precision of the flash makes it hard to ignore that possibility. Even NASA's internal logs quietly flagged the event. Though no public release was made, observatory insiders noted a temporary classification change in their tracking report, from natural reflectance anomaly to confirmed recurrence with polarization match. That may seem like bureaucratic language, but between the lines, it says this: they don't know what it is, but it's not noise, it's not a glitch, and it's not an accident. So now we're left with a puzzle, a comet that reflects like a mirror, twice, at the same angle, from the same location, under stable spin conditions, with no visible debris. Whatever's flashing at us from 3i Atlas, it wants to be seen, or at the very least, it doesn't care if we notice. Rotation is supposed to be reliable. For comets, it's often one of the first measurable behaviors. You track brightness variations over time, measure how long it takes the same surface features to swing into view, and plot the rhythm. It gives you a baseline, a fingerprint, something solid. But on December 8th, 3i Atlas changed that rhythm. And it did so without warning. Astronomers from the Las Cumbres Observatory in South Africa were among the first to spot the discrepancy. Their instruments, which had been locked on the object for weeks, showed a subtle shift in the light curve, not the intensity but the timing. The usual peaks in brightness that mark the comet's rotation began arriving early, not by much, just a few minutes at first. But over the next 6 hours the pattern kept accelerating. By midday, the rotational signature had tightened by nearly 8%, a measurable compression in period. This wasn't just noise or weather interference. Observatories in Spain and California confirmed the same thing. The object was spinning faster. Natural explanations came quickly. Some suggested a fresh outgassing event, a burst of sublimated ice from beneath the surface, jetting material and creating torque. That can happen. We've seen it with Comet 67P and others. But those events leave a mark, a visible jet, a distortion in the coma, or a tail flare. With 3i Atlas, nothing changed visually. No outburst, no visible ejection, just the spin, and it was clean. Even stranger, the light curve remained smooth. Normally, a sudden change in rotation would cause the brightness to wobble, irregularities from the shift in angular momentum. But 3i Atlas stayed stable, like it had anticipated the shift, or initiated it deliberately. And that's where the discussion turned. What mechanism could cause a sudden, silent change in rotation without disrupting the object's structure? Some suggested internal mass redistribution, like a shift beneath the surface, changing the moment of inertia. That's theoretically possible. But for that to occur, the body would need to have loosely bound inner components, something like a rubble pile held together by weak gravity. Yet 3i Atlas shows no signs of tumbling, no signs of stress. Its axis stayed locked. Another hypothesis was even more provocative: active control. If part of the object can adjust spin by deploying a vent, extending a mass arm, or manipulating its center of gravity, then this change might not be natural at all. It might be navigational, a shift in rotation to prepare for orientation, to face something, to realign. That theory gained traction when radar observations from Goldstone hinted at something even stranger. The object's radar cross-section also shifted, subtly but consistently, in a way that matched the rotation change, as if a surface feature, or structure, had reoriented with the spin. This wasn't just a faster rotation, it was a coordinated one. And here's the most important part. The rotation period stopped changing. After stabilizing at the new, faster interval, the object held that spin precisely, down to the minute, for the remainder of the observation window. That's not random. Natural forces don't tune themselves to a clean plateau like that. They decay, they spike, they wobble. But 3i Atlas adjusted, and then held, as if whatever made it spin faster had finished its job, as if a new mode had been activated, and when rotation becomes an action, not a symptom, the object stops being a rock in space, it starts being a system. Comets are messy travellers. Their wakes, those long ghostly trails of gas and dust, are usually chaotic. They widen over distance, diffusing into space like smoke from a drifting fire. The farther you look behind them, the more scattered and irregular the particles become. That's the natural rule. It's what we expect. It's what the models demand. But 3i Atlas didn't follow that rule on December 8th. Its wake did the opposite. It narrowed, and not gradually, but suddenly, with precision. At exactly Joe 613 UTC, a sequence of high-resolution composite images taken from the Subaru telescope in Hawaii showed something that startled even seasoned observers. The wake behind 3i Atlas, which had previously fanned out across a wide arc, appeared to constrict into a sharper, more collimated shape, like a soft blur being pulled into focus. It wasn't just thinner, it was organised. For over 3 hours, the dispersion rate of dust and gas trailing the object decreased significantly. Instead of drifting outward in a cone, particles clustered into a tighter central band, as if pulled inward. The most sensitive instruments showed a measurable reduction in lateral spread. The wake had lines, it had symmetry. And most unsettling of all, it maintained alignment. One working theory suggests magnetic channeling. If 3i Atlas is emitting a faint magnetic field, it could theoretically influence charged particles in its own debris stream, guiding them along field lines. But the field required to do this, across such a wide structure and at that distance, would be enormous. Too enormous for a natural comet. Another theory floated in closed-door discussions involves electrostatic cohesion, the idea that particles in the wake are somehow binding or reacting to changes in the solar plasma environment. But that too falls short. The shape was too smooth, the transition too fast, and the effect ended too cleanly. Because after 3 hours, it reversed. The wake returned to its original shape, wider, noisier, unstructured. The constriction ended as suddenly as it began, like a system turning off, like a switch. And that's the detail scientists can't shake. Natural processes don't usually snap back. They fade, they settle. But 3i Atlas's wake behaved like an aperture, opening, tightening, and relaxing with deliberate timing. It's hard not to draw a parallel to propulsion systems. Some researchers have privately compared the refocused wake to exhaust behavior seen in testbed plasma drives, where energetic particles are funneled through magnetic nozzles to produce directional thrust. The visual signature is eerily similar, a narrowing column of accelerated matter maintained under precise magnetic control. But even that analogy doesn't fully capture what we're seeing, because 3i Atlas isn't just projecting a narrow wake, it's adjusting it mid-flight, without changing course, without any visible jets, and without fragmenting under pressure. What kind of natural object does that? And there's one more troubling clue. During the narrow wake phase, the spectral profile of the debris shifted, not in composition, but in temperature. The material cooled slightly, even though solar exposure remained constant. It's as if the particles were being shielded, or, more mysteriously, accelerated in a way that reduced their energy footprint. That shouldn't be possible, unless the wake itself is being managed. And if the wake is no longer just a byproduct, but a controllable structure, then 3i Atlas may not be moving passively through space. It may be testing something, or practicing something, or sending something downstream and reeling it back in. In either case, the conclusion is the same. That wasn't a tail, it was a tool, and tools have users. At first, it was dismissed as coincidence. A faint electromagnetic pulse, buried in background noise, too regular to be natural, but too subtle to be confirmed. It was first noticed days before 3i Atlas passed Jupiter, then again in late November, but the signal was inconsistent, weak, intermittent, and no one wanted to leap to conclusions. But on the morning of December 8th, everything changed. The pulse returned, and this time it was on a schedule. 3 independent monitoring stations, one in New Mexico, one in Japan, and a third in South Africa, all logged the same anomaly within minutes of each other, a clean spike in low-frequency radio emissions originating from the approximate position of 3i Atlas, appearing in precise 48-minute intervals. The duration of each burst was short, just under 4 seconds, but the amplitude was clear, too structured to be thermal noise, too timed to be background radiation. It wasn't random, it was rhythmic, and it repeated 6 times across the night sky. What's more, the pulse wasn't just a spike in power, it carried a specific shape, a waveform that flattened slightly on its trailing edge, as though modulated or filtered. This wasn't typical of natural bursts which tend to arc and decay unpredictably. This pulse had corners, symmetry, a consistent rise and fall. So what could cause it? One explanation is that the object is interacting with the solar wind, triggering plasma oscillations as it cuts through the heliosphere. That can create electrical disturbances, but they're rarely uniform. Another theory suggests internal resonance, some kind of rotating mass or charged core discharging energy at regular intervals. But for such a rhythm to hold, the object would need to be internally stable, engineered even. And that's exactly what worries the research teams. Because when you observe a cosmic body emitting a repeating signal at a mathematically clean interval like 48 minutes, you're forced to reconsider what you're looking at. This isn't something tumbling through space shedding ice and rock. This is something doing something, on purpose. More unsettling, the frequency band of the signal overlaps with known communications ranges. Not exact matches, but close enough to be flagged. In fact, one research group at MIT noted that the waveform shape loosely mimics a slow beacon handshake. Not encoded data, not language, but the kind of binary-like rhythm that automated systems use to ping for feedback. And yet, there's no response. No return signal, no variation, just the pulse, every 48 minutes, like a heartbeat. What makes it even harder to ignore is its consistency across distance. As 3I Atlas moves farther from Jupiter and closer toward Earth, the pulse strength has not decayed proportionally. That means one of 2 things is true. Either the source is compensating, adjusting output to maintain strength, or the medium isn't interfering as much as expected. Either option is strange, neither is normal. Some scientists are now quietly calling this the Metronome event, a name that speaks to its uncanny regularity. It's not the behavior of a natural object but of a clock, a system counting time, a signal being maintained not because of nature but because of purpose, and the implications are enormous. If 3I Atlas is producing these pulses intentionally, it might be signaling to something else, or aligning with something, or calibrating an internal process we don't yet understand. But if it's not intentional, then it's still a system. And that raises the final, sobering question. What happens when the pulse stops? Not all mysteries in space announce themselves with a flash of light or a shift in trajectory. Some whisper through the dust. On December 8th, deep spectrum analysis of the material trailing behind 3I Atlas delivered an unexpected result. Using polarimetric backscatter from instruments in Chile, and supported by data from the Herschel array, researchers reconstructed a grain-size distribution model for the Coma and tail. It didn't match anything we've seen before. Normally, cometary dust follows a predictable pattern, a chaotic mix of fine particles, ranging from microscopic grains to fragments roughly a millimeter in size. The balance always favours the small. As a comet approaches the Sun, surface ice sublimates, pushing these particles outward. The result is a wide spread, both in size and in spatial distribution. But with 3I Atlas, the small grains are missing. That's the anomaly. Over 87% of the dust particles measured in the Coma were larger than expected. Not only that, but they were consistent in shape and size. Researchers found unusually narrow variation, grains clustering tightly around a single diameter, roughly in the range associated with engineered materials, not just big, but uniform. In natural systems, this almost never happens. Sublimation produces randomness, ice cracks, material flies off, and chaos takes over. What 3I Atlas is showing looks more like filtration, as if only specific grains are allowed to exit, or are being retained deliberately. And then there's the shape. Spectrographic returns hinted that many of the grains weren't round or amorphous like normal dust. They exhibited flat facets, regular edges, almost crystalline reflection patterns. That shouldn't be possible, at least not without extreme heat and pressure, neither of which are known to exist in the outer layers of a comet. This leads to 2 possibilities. Either the dust was altered after release, shaped by some exotic process we don't yet understand, or it was already that way before it left. And that's the unsettling part, Because if these particles began as uniform faceted structures, it means they were part of something ordered, something built, not fractured randomly but composed deliberately. Even more bizarre, the grains showed unexpected resistance to solar radiation pressure. They didn't scatter the way they should have. They followed tighter paths. Some even seemed to slow down relative to the wake. That implies magnetic interaction, or embedded mass. In one speculative paper circulating among researchers, a bold theory has emerged. The particles could contain internal structure, like hollow cores or layered interiors, the kind of complexity seen in microfabricated materials here on Earth. Not conclusive proof, but strange enough to push the conversation forward. What makes this dust even harder to explain is the absence of associated gas. Normally, dust ejection is accompanied by volatile outgassing, carbon compounds, frozen ammonia, traces of methane. But those signatures are weak around 3I Atlas. It's releasing dust, without the usual chemical fog. That breaks another rule. And now a bigger picture begins to form, a wake that narrows, a flash that reflects, a pulse that repeats, and now dust. Not of random chaos, but of structure. Something is choosing what leaves this object, or preventing most things from escaping. Either way, the message is clear. This isn't natural shedding, it's curated. And here's a chilling observation. Across all recorded interstellar visitors, from Oumuamua to Borisov, we've never seen grain uniformity like this, not once, not even close. But now, for the first time, dust is no longer just debris. It's a signature, a fingerprint, and maybe a message. Because randomness doesn't repeat. But intelligence? It leaves patterns in the smallest places. Space doesn't lie. It obeys motion. A body set on a course through the void will stay on that course, barring one of three things: a collision, an external force, or a decision. For weeks, 3I Atlas held a tight, predictive path through the solar system, threading past Jupiter, bypassing Mars, and heading deeper into the inner region. Observatories across Earth had locked in the object's ephemeris. Supercomputers modelled its arc with sub-pixel precision. Even with its strange behaviour, its physical motion remained stable, until the morning of December 8th. That's when the deviation appeared. It was subtle, just over 700 thousandths of a degree, an almost imperceptible shift in its long-range vector. But in interstellar terms, that's a lot. That's the difference between a bypass and a proximity event, between a drifting visitor and an intentional arrival. What triggered the change is still under debate. There was no impact, no gravitational slingshot, no detectable ejection of mass. And yet, the trajectory changed as if something pushed it. Not hard, not suddenly, but with a smoothness that matched active correction. The most telling detail. The curve wasn't random, it was clean, arsed, mathematically sound. Trajectory analysts at ESA first caught the deviation during their scheduled position sweep, when they compared projected position markers from the week before with the live track. The object had pulled slightly inward, a soft drift toward Earth's orbital corridor. NASA confirmed the shift within hours, and this was no ordinary drift. It wasn't caused by solar wind or uneven heating. The change matched no known non-gravitational forces. It wasn't tumbling, it wasn't chaotic, it was guided. That distinction has massive implications, because if a comet's course changes naturally, we can almost always trace it to a venting jet, an impact fragment, or a gravitational handshake. But if it changes without any of that, then what's left? Intention. Or influence. And that's where the conversation becomes uncomfortable. Could 3I Atlas be under active control? Could it possess internal systems that stabilize or adjust its motion? It's a question that no one wants to answer directly, not in public. But behind closed doors, institutions are simulating exactly that. An object with onboard guidance, capable of soft vector steering. What's more, the shift aligns with previous anomalies. The narrowing wake, the pulsing emission, the structured dust. All point toward an object that behaves less like a rock and more like a craft. Even more troubling, the new trajectory, while still safe, reduces the Earth-Mist distance in nearly every modelled case. Not by much, but by enough to matter. Enough to raise eyebrows, enough to reactivate old protocols, some of the same protocols that were quietly opened during Oumuamua's pass and promptly shut again. And yet, 3i Atlas hasn't made any sudden maneuvers since. Its adjusted path now holds steady. The correction, whatever its source, was one and done, like a course lock. And here's the thought that's keeping people awake at night. If this was a correction, then it means there's a target. And if there's a target, there's a plan. And plans don't belong to rocks, they belong to systems. So what does it mean when something from outside our solar system crosses billions of miles, and only then makes a final adjustment? It means it knew where it was, and it knew where it wanted to be. By the time most of the world wakes up, the alerts are already buried in research logs, timestamps, observation logs, frequency plots, no press release, no conference, just quiet entries in institutional databases, with subtle flags that only a few people know how to interpret. But within those circles, the ones that monitor anomalies, track spaceborne irregularities, and compile interstellar signatures, something has shifted. They're whispering again, and this time it's louder. December 8th wasn't supposed to be extraordinary. Another day of tracking 3i Atlas, another sweep of the Coma, another update on the pulse, but across observatories, labs, and mission control centers, there's an unspoken realization settling in. This object is no longer just interesting. It's becoming undeniable. Too many patterns are stacking. Too many rules are breaking. From the symmetry of its wake to the engineered behavior of its dust, from the clean pulses to the sudden vector shift, every isolated anomaly might be explainable, barely, with stretched physics, but together they form a profile, and that profile feels designed. Researchers who were once cautious are now hesitant for a different reason. Not because they doubt, but because they don't anymore. They're choosing their words carefully, calling it non-standard, saying things like requires further investigation or uncharacteristic acceleration behavior. No one wants to be first, but no one wants to be last either. Behind the curtain, the conversations are changing. Leaked memos refer to proactive monitoring. Agencies are cross-comparing their instrument baselines. Observatories that don't normally coordinate, especially private ones, are now syncing schedules, and institutions known for their discretion are quietly hiring specialists in areas that have nothing to do with comets, experts in propulsion, experts in signal analysis, even exobiology. And through all of it, the public remains mostly unaware, because official channels remain silent. Press briefings stay focused on solar weather or upcoming eclipses. Any mention of 3i Atlas gets filed under routine monitoring, if it's mentioned at all. But inside the halls of science, the tension is unmistakable. People are speaking in half sentences, slipping into corners, reviewing data off-network, because the last time this happened, with Oumuamua, it was too soon. The evidence was too soft, the object too fast, too quiet, too far away. And back then, most dismissed the possibility. They laughed, shrugged, moved on. But now, they're not laughing. Now they're watching an object that reflects light in ways that violate chemistry, emits pulses like a signal, leaves behind structured debris, alters its path without ejecting mass, reorganizes its tail, and does it all without fragmenting despite solar pressure that should have torn it apart. And still, no public statement, no unified theory, no denial, just whispers. One researcher at a major institution, speaking anonymously, said it best. We're past the point of coincidence, but we're not past the point of fear. And that may be the real reason the world hasn't been told yet. Not because it's uncertain, but because it's too certain. Because once something crosses the line from curiosity into pattern, from randomness into rhythm, it forces a question most institutions aren't prepared to ask. What if this isn't a visitor at all? What if it's returning? And what if the silence isn't coming from space, but from us?